And I will try to post the recording very soon. Sorry for some students have been reminding me, and I apologize for posting the assignments not immediately. So in the previous class, we were looking at two different samples, and we were performing these hypothesis tests for two different means. So, and we were assuming that the sample was big, meaning we had 30 or more elements in our sample, or we already knew the value of sigma. So we need to know that these samples are coming from a normally distributed population. So when we have sigma, or when we have more than 30 elements in our sample, so we are going to be able to approximate to the normal distribution, or use the normal distribution to to test for the difference between two means. So in this second part, we are going to assume the same thing. We're going to assume that we are going to take two samples. We're going to compare these two samples, and we are going to test the difference between the means. But in this case, we don't have a big sample, and we don't have sigma. So we know that when in the absence of sigma and in the absence of a big sample, we can use the t-distribution. So it's going to be no problem using the t-distribution to test the difference between these two means, right? So if a sample size less than 30 are taken from a normally distributed population, so now we are going to, as we did before in the confidence intervals and in the one and the hypothesis test with the one sample, in this hypothesis test for two samples that are small independent samples, we're going to be able to use the t-test. So, and we are going to test the difference between the population means. So we have made comments, or I have made comments on this. In many cases, in many cases, these small samples are taken in pilot studies. Some pharmaceutical companies, some people who are testing clothes or doing some small, they want to gather information whether running a bigger sample is worth it. So in many cases, these small independent samples, or in many cases, small samples are used, and they don't provide a big degree of inference, but in many cases, you can use those small samples to test different issues. So if the results are positive, meaning we find support for our claim, so then we can proceed to a bigger experiment. So that happens in many, many cases. So in order to use the t-test, there are three conditions necessary for the use of the t-test for small independent samples. First of all, samples must be randomly selected. We have talked a lot about randomness. Once again, when we have random samples, that yields results that are unbiased. So if we have a non-random sample, very likely we are going to have some degree of bias. So in this case, the samples have to be independent, and each population must have a normal distribution. So those are the assumptions that we need to consider. So in this case, so we can test the difference. So the test statistic, once again, is going to be given by the observed difference between the mean values of the two samples. So the t-test, this is the standardized test statistic, the one that we obtain when we are using our data. So it's going to be given by the observed difference minus the hypothesized difference. Once again, we don't consider this hypothesized difference. So our computations are going to be the observed difference by the degree of variation. So we are going to use, once again, the standard error to compute the standardized test statistic. So in this case, using the t-score. So the standard error and the degrees of freedom of the sampling distribution depend whether the population variances are equal. So we can make some assumptions, and we in some cases we know that populations variances are different, or we might know that population variances are equal. So those are assumptions that we need to know in advance. In this case, for the class, we are going to assume that, well, we are going to build the two cases when variances are equal and when variances are unequal. So it looks like a big thing. So the first case, 2-sample t-test for the difference between means, we are assuming that the variances are equal. So information from the two samples is combined to compute the pooled estimate of the standard deviation. So in order to find this little animal here, we have to, first of all, consider whether the variances are equal or not. If the variances are equal, so we are going to use this formula. So first we have to find the pooled estimate of the standard deviation. And then we are going to multiply it for the square root of 1 over the sample size in sample 1 plus 1 over sample size in 2. So as you can see, this is a big number, right? It's not that difficult. I think if we take a look at the elements of the pooled estimate of the standard deviations. So here we have the degrees of freedom times the standard deviation, the variance of the sample, plus the degrees of freedom in the second sample. Well, this is the degrees of freedom in the second sample multiplied by the variance in the second sample. So by the sample variance. So we have degrees of freedom times the variances in the samples. And that is going to be divided by n minus sample 1 plus sample 2 minus 2. So that is the degrees of freedom for this sample, the degrees of freedom for this sample, and this is going to be the degrees of freedom for the whole experiment. So you are going to see what I mean by that. So we have to be very vigilant for that. So so in this case, I am going to measure the variance of the first sample, and I am going to multiply it by the degrees of freedom of the first sample. If I have n equal to 10, for example, so my degrees of freedom is going to be 9. So multiply by the variance in the first sample. Then I have the variance in the second sample that is going to be multiplied by the degrees of freedom of the second sample, which is n minus 2. So in this case, we assume that n was, let's say, 10. So we have 9. Let's say that we have a second sample with 12. So we are going to have 9 and here 11, right? So when it comes to these big degrees of freedom, so we are going to add the first sample plus the sample size of the second sample, and then we are going to subtract by 2. So if we have 9 here and 11 here, so it's 9 plus 11 minus 2. So we have degrees of freedom for the sample 1, degrees of freedom for sample 2, and this is the degrees of freedom for the entire experiment, right? So once we get this pool estimate of the standard deviation, we're going to proceed to find the standard deviation. So this is the actual standard deviation. So we are going to multiply this big sausage times this. And as I said before, the degrees of freedom for the entire experiment is going to be given for n1 plus n2 minus 2. So in this case, I said this is 10. So we have 9. This is 12. We have 11. So this is for each sample. When we are accounting for the whole sample, we have 10 and 12. We are going to have 22 minus 2. So we are going to have 20 degrees of freedom. I'm going to show you exactly what I mean by that. So just keep in mind, this is one aspect of the t-test for the difference between means when we have equal variances. But sometimes the variances are unequal, and we know that. So the population variances are not equal, then the standard error is going to be given by this, right? So the standard error for the two-sample t-test for the difference of the mean when the variances are not equal, the standard error is going to be given by the variance of sample number 1 divided by the sample size of number 1 plus the variance of sample number 2 divided by the sample size of number 2, and then we take the square root. So as you can see, these formulas are very easy to do in Excel. I'm going to show you how I did it. So that's going to be very, very simple. So this is the first thing. We need to know whether the variances are equal or they are not equal. So, and that this case we have already discussed it before. Are both sample size at least 30? If the answer is yes, we have no problem. We use the C-test. If the sample is less than than 30, so are both populations normally distributed? If the answer is yes, we are both population standard deviations known? If they are, if I know the standard deviation for the population standard deviation for a sample less than 30, I still can use the C-test. But if it's not, so the first question, when the sample is less than 30 and we don't have information on sigma or the standard deviation of the population, so the first question is, are the population's variances equal? If the answer is yes, we use the long formula. If the answer is no, we use the small formula. And remember, these two different animals also have different degrees of freedom. We have to be very careful in the formula. Locally, I am giving you a nice Excel way to do it, okay? So we are gonna do this part. Are the population variances equal or unequal, okay? So let's continue. So this is the step-by-step. Remember, every time we see the statement, we have to convert this verbal statement into mathematical. Remember, H naught is the hypothesis that we are going to prove for this proof, and the H sub A is going to tell me the type of test. If we have less than, greater than, or non-equal, so we know that implies a different type of test. We need to know the level of significance, 5%, 10%, 1%, and then we have to make sure that we know how to compute those degrees of freedom. So for samples that are, so we have two different formulas for degrees of freedom. We need to know whether the samples are equal or they are not equal. So in the second case, I explained the formula, but I didn't say that when the variances are not equal, so to compute the degrees of freedom, we are gonna compute the lowest, we are gonna use the lowest of the degrees of freedom. For example, in the first case I was mentioning, N was 10, so we have 9 degrees of freedom. In the second, I said we have 12, so we have 11 degrees of freedom. So of course, 9 is lower than 11, so we are gonna use 9 as our degrees of freedom for computing the value of my critical values. So in this case, to compute the degrees of freedom, we have to use the smallest degrees of freedom arising from the populations, from the different samples. So that's what it says here. So then we find the critical values, we determine the rejection regions, then we compute the standardized test statistic. Remember, we are gonna do the observed differences minus the hypothesized differences. We don't care about this, so we are gonna do the observed difference by the degree of variation. Once again, in order to compute those values, we need to know whether are equal or non-equal variances. So then we are gonna compare our t-test with the rejection regions. And if it falls inside the rejection region, we reject. Otherwise, we fail to reject. We make the interpretation in the context of the original claim. So, so in this case, this is a very simple case. Before explaining this, I'm going to show you something that I did here. So, and it doesn't mean that you cannot do it. I am sure that you could have found this thing easier than what I did. So here, as you can see, we have independent samples and we have the t-test, right? So we have the case for equal variances and the case for non-equal variances. But what if you are given why if you are given a data set? For example, you are given these values. So I'm using the same values as before. As you can see in the previous case, we had a sample that was very big. In this case, we have only 20 observations. So in the independent large samples, we have like 30 something observations. In the second one, we have the independent samples that are small. So did you guys were able to download the data analysis app, the data analysis app here in Excel? Did you guys were able to download the data analysis web app? Add-ins is called. Well, if you didn't, you don't have to.
I did actually.
Say that again.
Yeah, I did.
Okay, good. So those who couldn't do it, please stay with me at the end. I'm gonna briefly explain and probably find some information online. That's very easy because what if you are given a data set, so you can use the data analysis. For example, I already said if you have a Mac computer and you have Excel, you can find the Excel add-ins, and then you can add the analysis toolpack. That is called analysis toolpack. So if you don't know how to do it, look at the type of computer you have and ask Google how to install the analysis toolpack in your Excel package. I think even if you are using if you are using the version online, it should work. It should work. So this is very simple. We have the data analysis. I want to do a t-test, 2 sample, assume equal variances, right? Very easy. I am gonna erase this because I did it twice. So to make sure that it works. So so this is a 5%. So first of all, I am assuming that the variances are equal, right? Of course, I have to do my hypothesis test and tell. So what is the goal of this? But just to perform the case, so we are gonna do the sample number 1. I'm gonna do the ranges. As you can see, I already click on the labels. So that means that because I am including the first one, the first cell, so I can use labels. So then the second one is going from, again, my data. So the hypothesized mean difference always is going to be 0. So remember that that's what we are assuming, that there is no difference in the means. So we are using an alpha equal to 5%. I can use an alpha 1%, right? So, and in order to put my, so I can do this in a new worksheet. So something is gonna pop up here, but I like to do it next to my data so I can see the results very easily, right? So, so we are gonna click OK, and we already have all the values. So of course, we have a t-statistic. So this is the t-score, the test statistic that I found using my data. As you can see, I have values here regarding means and variances, the number of observations, so the hypothesized mean, so the degrees of freedom in this case. So we have 21, 21 minus 2. So N1 plus N2 minus 2. So those are the degrees of freedom. So I have the t-statistic. So what I can do here is the following. So once again, these values are very close to each other because we are using the same data, right? So this is, let's say I want to do a two-tailed test. So I have values for one tail and two tails. So my p-values are very low. As you can see, if you look at this scientific notation, the decimal point is 44 points to the left. So the probability that I am committed a 1% error is extremely low. So my critical value for one tail test is, in this case, 2.42 minus, because I am using the left tail test, and my T statistic is 71. So if I make this longer, so this 71 is going to be somewhere in here. So the probability that this value is going to be close to 0, or I'm making a big mistake, so is very low. So I can prove this by looking at my T-stat compared to the critical for one tail. So I can use the critical for two tails. So my critical value is going to be 270 compared to the minus 71, same result. So this is the rejection region, remember. But we can just look at the p-values. So these p-values are very low. So that tells me that the probability of, like, so remember, p-values less than alpha. So then I reject H0, right? So in this case, my p-value is very, very low compared to the alpha 1%. So this p-value is 44 decimal points to the left. So I have all the reasons to reject my claim, to reject H0. And if my claim was the H sub A, probably I will be able also to reject, to support the claim. So, so this is what we can do. So this is for assuming equal variances. These results are not going to be significantly different from assuming unequal variances. So in this case, I'm going to also use the unequal variances case, which is exactly the same thing that we did before. So go to data, go to data analysis, and you can use the assumption that they are unequal. So in this case, it's just to show you the results are not extremely different from each other. And so I'm going to use again range number 1. So then number 2. So I'm sure that you will have some of these cases in your examples in Excel, in sampling learning. So we have an alpha, we set the alpha to the 1%. And in this case, I want the output to be here, right? So very simple, we can build this case very simple. And because we are using the same data, so of course the T statistic is going to be exactly the same, but the critical values and the p-values are going to be different, right? So in this case, the p-value is here, we have to move the decimal points 44 points. Here we have to move the decimal points only 30 points. So this data is very easy to look at. And so those are the critical values that we are looking at, and compared to the critical values for the two-tail test. So remember, if we are using critical value with one tail, we take this value as, if it's a left tail test, is negative. If this is a right tail test, this is positive. So same thing for this. So in this case, so it's very simple. So let me show you how we do this in Excel using the data that the book provides. So so let me go back to the example. Let me go back to the example. So the example that we're going to use basically is here. So example 2 sample t-test for the difference between means. So I here made this, as you can see, this is a formula, this is a formula, and those are formulas, right? So with these formulas, I am going to solve the standard error, right? So, and then the difference between the two sample sizes. So here, for example, the numerator is a formula and the denominator, which is this, so it's gonna be what is below. So in the denominator. So we are gonna be using, once again, we have the variances are not equal, okay? So let me go through the problem. The results of a state mathematics test for random samples of students taught by two different teachers at the same school are shown below. Can you conclude that there is a difference in the mean of the tests, the mathematics test scores for students for students of the two teachers use at an alpha equal to 10% and assume the populations are normally distributed and the population variances are not equal. So as you can see, you have a non-equal variances. So all we have to do in this case, let me move this a little bit, is that we are gonna be using this information. So the sample size here is gonna be 8 for the first, it's gonna be 18 for the second. The mean value is 473 for the first sample. And this value for the second is 459. So having this format in Excel is very convenient. So let's say that it says 473 and I put 373, right? So I can fix it and the formulas are gonna be corrected by themselves. So in this case, the value is 473. So my point is you can make mistakes and you can detect the mistakes very easily. So the standard deviation that we are gonna use here is 39.7, and in the second is 24.5, right? So as you can see, all these things are being populated. So we have a T statistic that is 0.92. So if we can do, but let's see. So here, so remember, this is a two-tail test. I wrote this Excel code, the T minus T dot IMV dot 2T. So this is for finding the critical value for a t-test with two tails. So if in this case, the alpha that we are looking at is 10%, I can type the alpha at 10%, 0.10, right? So, and because this is already asking, it's gonna give me the values for the two-tail test. So we have a T statistic that is 0.992, and this is 1.846. So what we have here is the following. So let me navigate a little bit to the bottom. So I'm gonna do this. So we have our T statistic, right? So because this is a two-tail test, so let me show you, I probably didn't make the case very clearly. So so the claim is that they don't have, the mu's are not equal. So that's the claim. So this is the complement. When we have the claim, the other one becomes the complement. So in this case, our H naught is the one that we are gonna prove for this proof. So if I reject H naught, then I have enough evidence to support the claim. If I fail to reject H naught, I don't have enough evidence to support the claim. So that's what we are supposed to do. So in this case, my T stat here and my critical value. So I have a 180, 89. So because this is 2 tails, I'm gonna do 1 and 2 tails. So the rejection region goes to this area, right? So this is minus 1.89, and this is plus 1.89, right? So this is the middle. So my test statistic is almost 1 standard deviation. It's gonna be here. Hold on. So it's gonna be, so it's gonna be somewhere in here, right? So this is 1, this is 0.92, right? Of course, this is outside of the rejection region, therefore we are gonna fail to reject, right? So so that is not, so that is outside of the rejection region, we are gonna fail to reject. So at the 10% level of significance, there is not enough evidence, as we said before, we are failing to reject, we cannot support the claim. So there is enough evidence to support the claim that the mean mathematics test score for the students of the two teachers are different. So, so of course, we did this very easily because, well, that can be done in Excel. So all we need in Excel is the sample mean, we need the sample standard deviation, and we need the sample size for the two cases. So in these two cases, so we just enter the data and we do the trick. So also make sure that the critical value, so just assume that this is only one tail test, right? Either left or right. So remember, for a one tail test to find the critical value, we have to exclude the tutti, right? So in this case, we have a 1.49. Still is outside of the rejection region, but so this is just to show you that here it was tutti, right? So so that is when we have non-equal variances. So we can have another case when we have equal variances. So so in this case, equal variances. So we can use the next case, equal variances. So also we need the sample size, the mean, the standard deviation. So all the formulas are here. And as you can see, in this case, I am doing just one tail test. So we can do also the two tail test if that is required. If we are doing one tail test, we use the negative for the left, we use the positive for the right, okay? So make sure that you understand that, because that is very important. So in this case, a manufacturer claims that the mean calling range in feet of a 2.5 gigahertz cordless telephone is greater than others and than of its leading competitors. You perform a study using 14 randomly selected telephones from one manufacturer and 16 random selected similar telephones for its competitor. So you are using 16 in one hand and 16 on the other hand. So in many cases, when we have two different groups, so this is one arm, this is another arm. So first arm, second arm. So in the first arm, we have 14 elements. In the second arm, we have 16 randomly selected phones. So the results are shown below. At the 5% level of significance, can you support the manufacturer's claim? So the manufacturer claims is that is greater than. So we are having a one tail test that is a right tail test, right? So so we are going to use the right tail test. So the results are shown below. Assume that the populations are normally distributed and the population variances are equal. So here we have also a very similar case to use. We need to know whether this is equal or non-equal. In this case, the problem is telling me exactly what I need to know, that the variances are equal. In real life, there should be enough information in the literature to know whether the variances are equal. So in many cases, when we are solving these kind of problems, and you don't have enough information, so you start Googling and finding papers that deal with these cases. For example, if I am using this difference in means, I can Google in some websites that are like Google Scholar, whether this another person has done experiments with these same issues, and whether they consider the variances to be equal or unequal. So in this case, so we need the sample size of the first, which is 14, the sample size of the second, which is 16. So as you can see, so we have degrees of freedom for the first, we have degrees of freedom for the second. So this is the two different samples. We need the degrees of freedom because remember, we have to multiply the degrees of freedom from one sample to with the variance. So that's the reason we need these values. So so we have a mean value of 1,275, and also we have a 1,250, right? So the standard deviation is 45 feet, and the second standard deviation is 30 feet, right? So as we can see, we have the values. So I have the t statistic, even I have a p-value. So if I am claiming at the 5% level of significance, I will say no. Here the p-value is greater than alpha. So I'm gonna fail to reject. Right here, I'm seeing that the level of significance is lower than my p-value. So once again, I know beforehand that I am gonna fail to reject the H naught. So, but still, I am gonna compute here. As I said, I am using a t-test. I need to know the values. So in order to solve this, so the t-test, remember, we need the probability and we need the degrees of freedom. So in this case, the degrees of freedom, I just typed 28, because I forgot to include this in the formula. So every time you have to do this, you have to enter your degrees of freedom. Or let me do this here, pardon. So let me do this. So the degrees of freedom for the degrees of freedom 1 and 2, right? So let's call it this way. So it's gonna be equal to sample 1 plus sample 2 minus 2, right? So that is 28. So that also should be a formula. So this formula. So I am gonna do the following. Instead of saying 28, I'm gonna click here. So every time I enter different values, my t-score is gonna be computed. And once again, make sure that in the two cases, you make the proper modifications, because we know this is a one-tail test. In the other case, we knew that it was a two-tail test. So for the two-tail test, remember, I added the 2t. For the one-tail test, I am not adding the 2t, right? So as you can see here is the t.inv. So I need probabilities. So in this case, is the 5%, 0.05%. And I have a critical value of minus 171. But remember, we are using, this is the value for the left tail test. We're assuming a right tail test of a 5%. So it makes sense that we use this with the different sign. So to make the long story very short, what we have here is the following. So we have our t-distribution. So we have a right tail test. In this case, I know it's a right tail test because that's what I know from the greater than. So my critical value is going to be 170. So So once again, I am using the positive value when it's right. I'm using the negative value if it was a left tail test. So I have a t-test that is 1/8. Huh, hold on. Oh, we reject H naught, but this is at the 5% level of significance. There should be something. So the p-value is, so probably this p-value have a little problem. So my critical value is 170. My t-stat is 181. Surprisingly, I need to find this value. So so we have a t-score. So we have a critical value that is 170. We have a t-statistic that is 181. So the t-statistic falls inside the rejection region. Therefore, we fail to reject. We reject H naught at the 5% level of significance. Let me see what happens with this. Am I doing the right thing? Oh, I see. So this is two tests, sorry. So this is a right tail test. I apologize. I made the wrong so T distribution, we have the 0.16 and the degrees of freedom is 0.7. Should be this one. Hold on. Let me rewrite this equation. So so equal. So we have the T that I M phi. We have the probability that is, no, this is the T stat. Ay, Dios mío. What did I do? So this is the T stat. So let me think about this because I'm getting confused. But here we did the right thing. We find the T statistic, which is the test statistic that we found using our data. And this is the critical value based on my alpha. So so in this case, oh, I see. This is the T statist. This is only for one. So X, no. So I have to review this formula. I think, hold on. What did we use here? T, that is 2T. K7 p-value. So let me check this part. I'm gonna send an email later because I think I made a little mistake. Because based on this, we reject H naught at the 5% level of significance, but I came up with a different p-value. So I will revise this and I will send an amendment very soon. So I apologize for this. So, but these computations are fine. So we were able to input the data and find the T statistic, which is this value. And this is the critical value. Remember, the critical value is the value that separates the non-rejection from the rejection region. And in this case, the T statistic falls within the rejection region. So at the 5% level of significance, there is enough evidence to support the manufacturer's claims that the phone has a greater calling range than its competitors. So, and that might be good because just imagine that you are the manager of your company and you have costs or some information from competitors and some information from your own store, and you are making a similar claim. So that might be something that you can do very easily. So once again, I'm gonna send an amendment for this because I think something is not very good. So so I will make an amendment. So so once again, So this is for the two tests, two sample t-test. So I'm very confident that if you use this with the t-stats and the critical value, you're gonna find the response. Also, if you use this, let's say that let's put this in hold on hold too. So if you use the critical value with the t-stat for the non-equal variances, so you're also gonna be fine and you are gonna be able to solve your problems. So I'm gonna send an amendment probably later during the day. So also, so this is also another case. So we saw the case where we have two different means, and those different means are coming from independent samples. So these two samples can be large with sigma or short, small samples without sigma. Now we know that the big samples, 30 or sigma known, we use the C-score. For samples smaller than 30 and without sigma, we are going to use the T distribution, but we need to know whether the variances are equal or the variances are unequal. So also this is using independent samples. But remember, we also make the comment that we have dependent samples, those samples that are paired. So we have the pre and the post. I want to know how well students are doing in my class. I do a pre-test and a post-test, and I'm gonna know whether they are doing fine. So, so this testing, this difference between means when the samples are dependent, we are also gonna use the t-test, right? So this t-test is gonna help me to find whether these two scores are bigger, or if I achieve the goal. For example, I am giving Lipitor to people that I know are suffering high cholesterol. So I give them before and after, and I am gonna see whether that helps with heart diseases and all these things related to high cholesterol. So in this case, we have a dependent sample. So this dependent sample, to perform a two-sample hypothesis test with dependent samples, we have to look first of all at the difference of each data pair. So that's the first thing that we're gonna do. For example, person number one, I'm gonna measure the cholesterol before and after. Person number two, cholesterol before and after. So if that is, so I have a number of people that I am doing this test. So so that's the first thing. I'm gonna find the difference between each of the pairs, meaning the pre and the post. So the test statistic is the mean of the differences. So I'm not gonna take the mean of each sample, I'm gonna take the mean of the differences. For example, if I have the person who has 130 and then 120, so I'm gonna measure the difference. So all my elements in my group, I'm gonna measure the difference, then I am gonna measure the mean of the difference. So D bar is gonna be the mean of the difference, which is equal to the summatory of the differences divided by the sample size. So it's a very simple way to compute the mean of the differences. We're gonna add the differences. So imagine that we have a column for the pre and then the post. So another one for the difference. So at the end, we are gonna add the differences and divide it by the sample size. And then we are gonna find the mean of the difference between paired data entries in dependent samples. So once again, we need the samples to be randomly selected. We need the samples to be dependent. And that means that we need the same number of elements in the pre and the post. So that is gonna make our life easier. Otherwise, we probably won't be able to compute those values. So, and also both populations need to be normally distributed. So if these requirements are met, then the sampling distribution for the difference for the mean of the differences is approximated by a t distribution with n-1 degrees of freedom. where n is the number of data pairs. So if we have 8 subjects, let's say in our study, so the degrees of freedom is gonna be 8 minus 1. So we have 16 different observations, but we have only 8 individuals. So my degrees of freedom are gonna be given by the number of individuals minus 1, okay? So those are the things that we need to find. So we need the number of data pairs, the number of pairs in the data, how many individuals, how many items, how many, so how big is my sample size, right? So I'm gonna find the difference, and then I'm gonna find the hypothesized difference. So so it's basically the same. The hypothesized difference is gonna be equal to 0. So that's the comparison of the means that I want to do based on my samples. So I need the difference, the mean of the differences that is found like this. And the most important part, well, not the most important part, one of the things that we also need to do is to find the standard deviation. So this standard deviation of the differences is gonna be given by this formula. So we can use this, we can use this. I build the formula to use this one. So we have the differences squared, then the summatory. So we build one for the pre, one for the post, one for the difference, and one for the squared differences. So I'm gonna build another column for the squared, the differences of the square of the differences, and then I am gonna add them. So then this is the summatory of the difference and then squared. So I'm gonna compute in the third column that I was mentioning the differences. Once I find the difference, I'm gonna square it. So that's gonna be, this is different from this. This is all the summatory of the difference, and then whatever the number is, I'm gonna square that number. Here, I'm gonna square each of the differences, and then I am gonna add them one by one. Then divided by the degrees of freedom and the square root. So it sounds like a tongue twister, but it's not that difficult. So, so the test statistic is gonna be the differences of the mean, and the standardized test statistic is gonna be given by the observed differences minus the hypothesized differences. Once again, that doesn't count, that makes me happy. And then the standard error is gonna be given by the standard deviation divided by the square root of the sample size. Once again, degrees of freedom in order to compute the critical values given alpha is gonna be n minus 1, okay? So, so I hope this is not that complicated. So let's see a case. This case is very nice because we have, so once again, we have to follow all these steps. So, so once again, in order to compute the mean and the standard deviation, we have to find this value. So once we compute the standard deviation of the sample, we have to divide it by the square root of the sample size. So this is one step. This is step number 2. So once I find the standard deviation, I divide it by the square root of the sample size, and then I will be able to compute my test statistic. So remember, the test statistic is given by the observed difference divided by the degree of variation. So the degree of variation is going to be given by the standard error. So then we reject if it falls in the rejection region and fail to reject otherwise. So this is the case, and this is actually a nice case. So let me also tell you that this is the basic. I built this case with using the table, the same results, so the same data. So in order to make this work, well, this table, unfortunately, is built only for the observations I have here. So as you can see, most of the data comes from the, so what I have here. My point is, if you have a different table, so probably you have to modify some of these, like for example, the degrees of freedom is equal to n minus 1. So before, which is the sample size, in this case, we have 1, 2, 3, 4, 5, 6, 7, and 8 people, right? So if I have 8 people, so I'm gonna use the sample size here, 8, and then the degrees of freedom is gonna be 7. So, so in some cases, some of these values are attached to the number of cells. So be aware of that. Hello? Can you guys hear me? Hello?
Yeah, yeah.
Okay, it seems that my iPads are dying, which is not good. Let me get rid of the iPads or whatever it's called. So let me unplug them. That is not, oh, it's, okay. So can you hear me now?
Yeah.
Yeah.
Okay, thank you. So this is the individual. So this is individual 1, 2, 3, 4, 5 until 8. So let's read the case. A shoe manufacturer claims that the athletes can increase their vertical jump heights using the manufacturer's new strength shoes. Just imagine that Mr. LeBron comes up with the idea that he jumps very high because he uses very specific shoes. And if you use those shoes, you are going to jump as high as Mr. LeBron. So how do you know? Well, we do I need to choose a big sample for that? So the answer is no. I mean, I don't have the needs for a big sample right now because it's an idea. It's a hypothesis that I am trying to develop. So I'm going to use a very small sample. I'm going to see what happens in the small sample. I'm going to apply my statistical tools to make sure that I am doing the proper inference. So if this small sample is good, probably I will be thinking about testing my shoes with a bigger sample, right? So that's what the small samples are good for. So the vertical jump heights of 8 randomly selected athletes are measured. So after the athletes have used the strength shoes for 8 months, their vertical jumps heights are measured again. So the vertical jump heights in inches for each athlete are shown in the table. So we have the table here with the different jumps. So the first person jumped as high as 24 inches. Now he or she is jumping 26. So the second, same thing. The third, no difference. The fourth, very little difference. The fifth is not doing very well. She or he jumped less than before. So we have different cases here. So how can I come up with a very strong argument that this is true? So assuming the vertical jump heights are normally distributed, is there enough evidence to support the manufacturer claims? So in this case, that is very important. Let me show you this because this is very important. So that's what I can tell you about these cases. For example, the oh, sorry, what is this? Ay, Dios mío, too many. So for example, the is low and the post is higher. For example, the is 10 and the post is 20, right? Just hypothesizing. So the difference in this is going to be minus 10, right? Because we are going to subtract the post minus the So I'm going to have a minus 10. So in this case, my hypothesis, the alternative is going to be that the difference, the mean difference is going to be a negative number. So I am expecting that, for example, if I want things to improve from the to the post, so that means that the difference is going to be negative, right? So then in this case, I am going to use less than. right? So that's what I can tell you so far. So, and also based on the data. So in this case, let's say that we have a pre of 100, well, let's use the same numbers, 20, and we have a post of 5. So this is going to be a positive 5, right? If I subtract the post minus the pre, so that is going to be a positive 5. So I can use in this second case a greater than. So I am expecting that the number that is going to come out after this is going to be higher. So that's what the hypothesis is telling me. So we are expecting the jump to improve from being 10 to being 20. So the difference is going to be negative. Therefore, I'm going to use a claim that uses the less than. So if the case was different, for example, this is the level of cholesterol, and if you take the pill, it's going to go down to 5. So then the difference is going to be 5. I'm going to use the greater than. So in many cases, the case is going to tell you, well, the person, the pre and the post are going to be equal. So in this case, we know that we are going to use a two-tailed test. So in this case, we are going to be using a one-tailed test because I am expecting the jump to be higher. So the expected difference is going to be less than. So that's what I can tell you here. So in this case, my jump before and after, so it's going to be a number that is going to be negative. I am hoping that this is good. So of course, after looking at the sample, I might be disappointed because everybody did not jump as high as I expected. So it's going to be very easy for me to reject the hypothesis. But in this case, the claim is telling me that they are expecting that the jump improves. Improve means they jump higher. So there might be also the case that the cholesterol improves, so the expected value is going to be less. So we have to read very clearly the statement, because based on that, we are going to make our case. So in this situation, we have this jump, the difference is going to be given by the before and after. So we have an alpha that is going to be 10%, and the degrees of freedom are going to be given n-1. So far we can compute very easily the t statistic, the critical value. So let's do the following. So in this case, I'm going to make some from here. So I type the values, as you can see, 24 and then 26. So those are the values. So 24 and 26, 22, 25. So the first thing I did was to find the differences, right? So in this case, I found the difference. I subtracted the after from the before. So I'm going to say before minus after. So as you can see at the bottom, I am adding, this is the sum of D, right? So this is the sum of D. Every time I have a difference, I'm going to have the cumulative number here. So because I built that formula to add all these differences. So remember, I need the, for my formula, I need the summatory of the differences, then divided by the sample size in order to calculate the mean of the differences. So in this case, I'm going to drag this down. So as you can see, that person didn't improve. This person did worse. So, but most of the people are improving their jumps. So the summatory of the D's is here. So remember, part of the formula, I also need the D's squared. So I'm going to find the D's squared here. So I'm going to square the difference. So I'm going to say this number, circumflex axle, 2. So that, remember, is to raise to the power of 2. So I'm gonna raise this number, I'm gonna drag this down, and here I have the summatory of the squares. So remember, we need the summatory of the differences squared. So this is the summatory of the differences squares. This is gonna be the summatory of the this and then squared. So once again, this is the summatory of the this squares. This is the this squares. So this number is gonna be raised to the power of 2, right? So so now I have enough information to include this. My level of my t score, so what do I need here? So my alpha here is going to be how much? So my alpha here is going to be 10%. So I'm going to do a left tail test. So my alpha is going to be 0.10, 10%. So here I have the critical value for alpha. So so this is using the normal distribution. So so we have the critical value. So we also need the summatory of this. So here, I regret that this is not big enough. So the summatory of the this is minus 14. So I'm gonna say equal. That's gonna be the number, the summatory of the this. So so this is the D bar. As you can see, I am computing the mean value for this, which is the summatory of the differences divided by the sample sizes. That's what we did. That's what we said before. So the summatory of the D's divided by the sample size. So this is going to be my D bar. So I need the summatory of the D's squares. So here, the summatory of the D's squares is going to be this value, right? So I'm going to say the summatory of the D's squares is going to be this. And then here is the sum of these, then square. So I'm going to sum all the these and then square it. So I'm going to say equal, click on this. So that's basically what I need to solve this case. So I have an alpha that is at 10% alpha. I have 8 elements in my sample. So I'm not counting the pre and the post, I'm just counting the number of individuals. So the degrees of freedom are going to be given by this. So I have the critical value and I have the test statistics. So here, hold on. So I am getting lost, tired, and hungry. Where I was. Okay, so those are the results. So here we have the case, we have the significance and the degrees of freedom. So let me see something that critical value. Why am I using the norm? This is the t-value. So I think I'm making also a big mistake here, which I'll also apologize. That should be the t in. So I need for one sample, I need the probability, which is this one. Hold on, let me raise this. Then I made also a mistake here, which I regret, of course. So the critical value is going to consider the alpha and is going to consider the degrees of freedom. So in this case, I'm going to use the t because we are using a t-test for one sample for a one-tail test, 10% and 7 degrees of freedom. That should be the value, 1.4, yeah. So I apologize, please correct this one. That should be the t distribution, I use the normal distribution. So sorry for that. So we have the t distribution. This is the critical value. So based on our case, this is the test statistic. So here, so we have a critical value that falls in, so this is the value. So after computing all these formulas, so we have a critical value of 2.33. So that's what, sorry, a critical value of 1.415, and we have a test statistic that is 2.33. So here, this is the test statistic, this is the critical value. So if we were doing this here, so I am going to do my t-distribution. So this is a left tail test because we are doing a left tail test. This is my rejection region. My critical value is going to be minus 1.41. And my test statistic is going to be 2.33. So it's going to be something like this, minus 2.33, right? So here is very clear that we are going to reject H naught. So in this case, we're going to reject H naught. So we have enough evidence to support the claim. So if the company is claiming that the shoes are very good and they help people to jump higher, so we can support that claim. So at the 10% level of significance, there is enough evidence to support the shoe manufacturer's claim that athletes can increase their vertical jump heights using the new strength shoes. So what I can do here, for example, I have a sample that, so let's say that I have a sample of 10. So that's what I was thinking about. Let's say instead of having 8 athletes, we have 10, right? So I'm gonna insert 2 more values, two more insert cells. Okay, so let's say this is gonna be observation 6, 7, and 8, right? So I'm gonna have patient number 9 and person number 10, right? So as you can see, we have done everything here. So most of these things are, for example, this one is the result of my D. So those values, right? So so let's say I have a 35, 40. We have a 23, 21, right? So we already have different values. So as we can see, the sum increase. So that's the value that we can see here. The 289 is also here, and the 85 is also here. So my point is, you can modify this. Let's say you have 10 individuals. Of course, you have to type them again. But these formulas are meant to help you find the values. So in this case, we can use only the 8 athletes that we were using. So, or we can add 2 more rows and add more data. So my point is, these values are going to be also here for a sample that might be bigger. So just make sure that you see where you have formulas and what these formulas mean, and then so make sure that you understand how this formula is built. You can do it very easily. So I think I'm going to stop here. Is there any question so far? Is there any question so far?
Yeah, Professor, I have a question.
Mm-hmm.
Can we talk